Hello friends, so today we are going to do part 2 of the questions which were asked in the year 2020, and they are total of 13 questions, and all these questions are from the mains only. And we also require part 3 for that to cover all the questions that will be from year 2020, and the part 3 will be consisting of mains as well as advanced questions. So first question: in a single slit diffraction setup, second minima are observed at an angle of 60 degree. The expected position of the first minima is. So we are given the position of the second minima, and we have to find out the expected position of the first minima with respect to the angle that is given as 60, that is theta is given to us. So you can say that for second minima, we can write the equation that t sine of theta will be equal to 2 times lambda, and theta is given to us as 60 degree. So we substitute the value, we get d sine of 60 is equal to 2 times lambda, and sine 60 is root 3 by 2. So we get that d root 3 by 2 is equal to 2 lambda. From here we can find out the ratio of lambda divided by capital D, and that will be equal to root 3 divided by 4. And we need to find out for the first minima. Therefore we can write that for first minima, we can write the relationship that d sine of theta will be equal to lambda, and from here once again we can find out our lambda by d. We can say sine of theta is equal to lambda by d, which we just calculated is our square root of 3 divided by 4. Therefore we can say our theta is equal to sine inverse of square root of 3 divided by 4, and we get from here that theta will be approximately equal to 25 degree. So option number 1 is the correct one. Option 1 is correct. Next question. We are given that if we need a magnification of 375 from a compound microscope of tube length 150 millimeter and an objective focal length of 5 millimeter, the focal length of the eyepiece should be close to. So we need to find out the focal length of eyepiece based on the magnification and the tube length along with the objective focal length. So in this case the position of image is not mentioned, so we have to divide it into 2 cases. First will be the final image is at the least distance of clear vision, and the second case will be the final image is at infinity. And in both the cases we are going to get approximately the same answer. Okay. So we start with that our final image is at least distance of clear vision. Distance of clear vision. And we can say that our magnification, that is capital M, will be equal to L divided by F naught, and this comes 1 plus D divided by our Fe. We substitute the values. Magnification is said to be 375, so we can say this is 375, and multiply by, okay, let me first substitute the values. 375 will be equal to length, that is given as 150, and divided by our 5, and this comes 1 plus D is given as 25, and we need to find out our Fe. So this will be coming as, this goes by 30, so we get 1 plus 25 divided by Fe is equal to 375 divided by 30. So we get our Fe is approximately equal to 22 millimeter. And for the second case, we can say that the final image is at infinity. Final image is at infinity. And under this condition, we can say our magnification is equal to L upon F naught and D upon Fe. And once again, we substitute the value. M is given as 375 will be equal to, and L we have our 150 divided by 5, and this is about 25 divided by Fe. And same, you can just cancel that out by 30, and from here we get our Fe will be approximately equal to 22 millimeter. So in both the cases the answer will be same, so option number 1 is the correct one. Option 1 is correct. Next question. We are given that the focal length of a convex lens in air is 16 centimeter and mu of glass is given as 1.5. Now the lens is submerged in liquid of refractive index 1.42. Find the ratio of focal length of the medium to the focal length of the air has a closest value. So in this case, we are going to use the formula that our focal length, that is 1 upon F for the air, will be equal to refractive index of glass divided by refractive index of air minus 1, and this comes as 1 upon R1 minus 1 upon R2. And similarly, we can write it for medium also, same formula, 1 upon Fm, only the refractive index is going to change. So we are going to refractive index of glass divided by refractive index of medium minus 1, and the radius of curvature is same, so 1 minus R1 and R2. And if we divide them, we get this as Fa upon Fm will be equal to, we have this as mu G upon mu m minus 1, and we get this as mu G upon mu A minus 1, and we substitute the values. 1.50, 1.42 minus 1 divided by 1.50 minus divided by 1 and minus 1, and this will be approximately equal to, this comes as 0.08 and divided by 1.92 and multiply by 0.5. Sorry, not 1.92 but 1.42, and we need to find out the ratio of medium to air. Okay, so we need to reverse it. So we can say our focal length of medium to focal length of air will be equal to 1.42 multiplied by 0.5 and 0.08, and this comes approximately equal to 9. So option number 1 is the correct one. Option 1 is correct. Next question. It says that a telescope has a magnification of 5 and length of the tube 60 centimeter, then the focal length of the eyepiece is. So we are given a magnification, and for magnification we already know the formula, that our magnification m is equal to the ratio of focal length of objective to focal length of eyepiece. It is given as 5, so this will be 5 FO upon FE. So from here we can say our FO is equal to 5 times FE. And we also know that the length of the tube is given as 60 centimeter. It means our FO plus FE should be equal to 60 centimeter. FO plus FE 60. We substitute the value, that is our 5 times FE plus FE is equal to 60, which gives us that FE is equal to 10 centimeters. So option number 1 is the correct one. Option 1 is correct. Next question. It states that if relative permittivity and relative permeability of a medium are 3 and 4 by 3 respectively, the critical angle for this medium is. So here we are given relative permittivity as well as relative permeability. Okay. So we are given basically epsilon of ER and mu R are given to us. Okay. We start from given data. So we are given a relative permittivity, a relative permittivity is given to us as 3. So from here we can find out the permittivity of the medium. You can say permittivity of medium which is represented by epsilon, and that will be equal to 3 times epsilon naught, and we are given also the relative permeability, and that is given to us as 4/3. So from here we can find out the permeability of the medium. Permeability of medium, which is represented in mu, and mu is equal to 4/3 multiplied by mu naught. And from here we can say that our mu times epsilon naught will be equal to, this comes as 4/3 mu naught times 3 epsilon naught. 3 and 3 goes away, and this comes as 4 mu naught times E naught. And if we find out the ratio, we can say that our mu naught upon mu naught E naught divided by our mu E will be equal to 1/4. And if we take square root both sides, we get this as mu naught E naught divided by mu multiplied by E. This ratio is equal to V upon C, and that will be equal to our square root of the right side, that will be coming as 1/2. And this is nothing but our critical angle. So you can say sine of theta C is equal to 1.2, and this gives us that a critical angle will be equal to our 30 degree. So option number 3 is the correct one. Option 3 is correct. Next question. We are given a plano-convex lens of radius of curvature 30 cm and refractive index 1.5 is kept in air. Find its focal length in centimeter. So we have a plano-convex lens and it is kept in a refractive index of 1.5. We need to find out focal length. That is directly based on the formula. That is our 1/f is equal to mu minus 1 upon r1 minus 1 upon r2. And it is a plano-convex lens, therefore r1 will be equal to over infinity, and r2 radius of curvature for the other side will be minus of 30, and mu is given to us as 1.5. We substitute the values, we get this as 1/f is equal to 1.5 minus 1, and this is 1 upon infinity minus minus plus divided by 30, and this gives us 0.5 divided by 30. Therefore our focal length f will be equal to 60 centimeters. Next question. It states that two immiscible liquids of refractive index square root of 2 and 2 square root of 2 are filled with equal heights h in a vessel. Then apparent depth of the bottom surface of the container given that outside medium is air. So we have two liquids which do not mix with each other, and they have equal height, and the refractive indexes are different. So we can just draw an approximate figure. Suppose this is our vessel and this is the surface, and we have a first liquid, height is given as h, and we have a second liquid, height its height is also given as h, and the refractive index of first one is, let us suppose this is called as mu1 is equal to square root of 2, and here we have mu2, that is 2 square root of 2, and we have to find out the apparent depth of the bottom. So apparent depth of the bottom will be equal to apparent depth because of the first liquid plus due to second liquid. We can say that apparent depth d will be equal to, we have h upon mu1 plus h upon mu2. We substitute the values, we get d is equal to h is same, so this comes h, so mu1 is our square root of 2 plus this comes h 2 square root of 2, and we can take h as common, h along square root of 2 we can take as common, so this comes 1 plus 1 upon 2, and this will be coming as 3 by 2, so this comes as 3h, and we have it as 2 square root of 2, and we can just rationalize it. And we get our d will be equal to, this comes as 3 root 2 divided by 4 multiplied by h. So we get 3 root 2 h divided by 4. Option number 1 is the correct one. Option 1 is correct. Next question. It states that if a point source is placed at a depth h in a liquid of refractive index 4/3, find percentage of energy of light that escapes from the liquid, assuming 100% transmission of the emergence light. So in this case, we are given that we have a liquid, a point source is placed at a depth h. So we can just draw an approximate figure. Suppose this is the height of the liquid, and we have a point source, and this point source will be able to, you can say, transmit the light something in this shape, like this, and beyond this point it will be nothing but a, you can say, resulting in the total internal reflection. Let us suppose this angle is our beta, so we can just call this angle will be also equal to our beta, and h is the height of the liquid, and we are given a refractive index of the liquid is given as 4/3, so we have mu is equal to 4/3. Therefore we can say that our beta, which is equivalent to our critical angle, so we can say beta is nothing but our critical angle. Therefore we can write that sine of beta will be equal to 1 upon mu. Mu is over 4/3, so this comes as sine of beta is equal to 3/4, and from here we can find out our cos of beta, which will be equal to 1 minus sine square beta and its square root, and we substitute the value, we get cos of beta will be equal to square root of 7 divided by 4. Now here we are going to use solid angle, and we know that the solid angle that is our d of omega is equal to 2 pi r square, and this comes 1 minus cos of beta, and here r is this radius, this is r, and we need to find out the percentage of the light, will be equal to, this will be coming as 2 pi r square 1 minus cos of beta divided by 4 pi r square, and we need to 100. We substitute the value, and this looks good, 4 pi square, and this goes by 2, so we can write this will be equal to 1 minus cos of beta divided by 2 and multiply by 100. We just found out our cos of beta, that is square root of 7 divided by 4, so we get this as 1 minus square root of 7 4 divided by 2 multiply by 100, and this we can approximate equal to 17%. So option number 2 is the correct one. Option number 2 is correct. Come to the next question, and it states that a spherical mirror is obtained as shown in the figure from a hollow glass sphere. If an object is positioned in front of the mirror, what will be the nature and the magnification of the image of the object? Figure drawn as schematic and not to the scale. So we are given a spherical mirror, and it is having an object placed somewhere here, and we have to find out what will be the nature and the magnification image. So we need to find out what will be the position that will be giving us magnification, and we are also going to find out what will be its nature. And so from this particular figure we can just make a approximation of that. This will be our 0. So we have a diameter of this sphere is equal to 16. So from here we can find out the radius of curvature, or the focus diameter is 16, radius of curvature will be 8. Therefore we can say we have the diameter is our 16 centimeter. Therefore our radius of curvature will be equal to 8 centimeter, and from here we can find out our focal length. Focal length will be equal to, or for this particular it will be minus, so we can say we get this as minus of 8 divided by 2, which gives us minus of 4 centimeters. Okay, and we can just approximate that our object will be close to somewhere around about 10, so we get our u will be equal to minus of 10 centimeter, we can use the formula directly now. That is our 1 upon V plus 1 upon U is equal to 1 upon F. We get 1 upon U, this is minus 1 upon 10, focal length is our 1 upon 4. So we get from here 1 upon V is equal to minus 1 upon 4, and this will become plus 1 upon 10. And we can just define that our LCM will be equal to 40. So we get 1 upon V is equal to 40. This comes as minus of 10, and this will be plus of 4, giving us minus of 6. So we get our V is equal to 40 upon 6. And we can just cancel it out, get by 3, and this goes by 20. So we get from here that our V is equal to minus 20 upon 3. And we can magnification, and magnification is equal to minus V upon U, which comes as minus V, just we found out, is minus 20 upon 3, and U we know is our minus of 10. So this comes as 2 minus minus and minus 2 by 3. So we get magnification is equal to minus 2 by 3. And so we can draw a conclusion that our V is minus 20 by 3. So it will be, the image will be on the left side. So image will be real. So we can say image is real, and nature and magnification. Okay. And it will be obviously inverted because of the negative sign. So we have inverted real, and we have our and unmagnified. Therefore option number 1 is the correct one. One is correct. Next question. And it states that a light ray enters a solid glass sphere of refractive index mu, that is given as square root of 3, at an angle of incidence 60. The ray is both reflected and refracted at the farther surface of the sphere. The angle in degrees between the reflected and refracted rays at this surface is. So for this we can draw an approximate figure. So we have a solid glass sphere. So this is our solid glass sphere, and this is the principal axis with the center at O. This is our center, and let us suppose ray is incident at this point, and the angle is given as 60, and it will be refracting to the further end. Let us call this as point A, this is point as B, and at the point B it says that it is refracted and reflected. Okay, so we can just draw a normal here. So it will be reflected, something like this, and it will be refracted, something like this. So this ray is our refracted, and this ray is our reflected. And the normal will be passing through the center of, so the normal will be passing through this. It should be ideally straight line. Let me draw it again. Like this, and we can just also draw it like this. Therefore, we can use Snell's law at A, and let us suppose this angle we call it as R. We can find out, and this is our incident angle, and this is our air. So here mu1 equal to 1, and this is mu2, that is our glass refractive index is given as square root of 3. So we can Snell's law at A. We can write mu1 sine of I is equal to mu2 sine of R, and mu1 is over 1, and we have a sine of 60. Mu2 is our square root of 3, and we have this as sine of R. We substitute the value, we get sine of 60 is square root of 3 divided by 2, and this is our square root of 3 sine of R. 3 goes square root goes by square root, so we get sine of R is equal to 1 by 2, which gives us that our R is equal to, this will be equal to 30. And let the angle between a reflected and refracted, let us call them as theta. So let us call this angle as theta, and we can say that our this angle, let us suppose we have alpha, so obviously this angle will be also our alpha. Therefore, you can say this angle will be equal to our twice of alpha. Second, let me draw this point B. So we have, this is point B, and this is normal, yes. So this angle will be equal to this angle, so we have this as twice of alpha, so this will be also equal to twice of alpha. Okay, and we just found out that our R is equal to 30 degree, so this is our 30, and we can say that our alpha So we can just write it that we have a 90-degree, and this will be giving us that our alpha will be equal to 30-degree. Okay, so we get this will be equal to over 60. So this angle will be also 60, and the angle between the two is our theta. So at point B, we can write it as 60 plus, so let me sort it out. So this total angle is about 2 alpha. So this will be our alpha, and this angle will be also our alpha. So we can say our alpha plus theta plus 60, and this alpha will be equal to 30. Now it's the correct one. Therefore we can write that our alpha plus theta plus 60 will be equal to 180, and we have our alpha is equal to 30. So we substitute it, 30 plus 60 is 90. So we get theta is equal to 180 minus 90, giving us theta is equal to 90-degree. So the angle between the reflected and refracted will be equal to 90 degrees. Next question. We are given that an observer can see through a small hole on one side of jar, radius 15 centimeter, at a point at height 15 centimeter from the bottom. See figure. The hole is at a height of 45 centimeter. When the jar is filled with liquid up to a height of 30 centimeter, the same observer can see the edge at the bottom of the jar. If the refractive index of the liquid is n upon 100, where n is an integer, the value of n is. So we are given the figure, and we are given that the height of the hole from the bottom is 45, and we have a height of, you can say, a point that is 15 centimeter, and that is seen when there is no liquid in it. And as soon as liquid is poured into this, and the height of that liquid is given to us as 30, so obviously refraction is going to take place at this point, and therefore the observer can see the bottom of this particular point. So ray of light will be traveling something like this, and we are given this 30, we have this as 45, 30, and we are going to get this will be equal to 15. And let us complete this part, and this will be also our 30. This will be our angle of refraction, and let us call this as angle of incident, that is our I. Therefore we can say we can find out this R by using the relationship that tangent of R will be equal to 15 divided by 30, which is 1/2, which gives us that our R will be equal to, okay, we can directly find out sine, we need not to find out the R, and therefore we can say from here that we have sine of R will be equal to 1 upon square root of 5. And and we are given that we have a radius 15 centimeter. Okay, and we can use, let us call this as point A, and we can use the Snell's law at A. Radius of jar is given 15, so this will be also 15. So these are 15, 15, so obviously this angle will be our 45. This is 90 degree, so we get our I will be also equal to 45. So you can say our angle of incidence, that is our I, will be equal to 45. Okay, because the radius of jar is given 15, so this will be also 15. So this is 15, 15. So we get that our this angle will be 45, giving us the angle of incident is equal to 45. And we can use our Snell's law at point A. Snell's law at A. So let us suppose this is our mu1, which will equal 1, and we have a this our mu2, which we need to find out. So we can write that our mu1 sine of I is equal to mu2 sine of R. Sine of R we just found out is 1 upon square root of 5. And angle of incidence we know is 45. Mu1 is our 1, so we can say sine of 45 is equal to mu2 upon square root of 5. Sine of 45 is square root of 1 upon square root of 2, so we get this as mu2 will be equal to square root of 5 divided by 2, which is approximately equal to 1.581. And in terms of n by 100, which is given to us, so we can say our n by 100 is equal to mu, or we can say that our n is equal to 100 multiplied by mu. In this case it is mu2, so we get 100 multiplied by 1.581, and n is a integer, therefore we can say that our value of n will be equal to, this will be our 100, and we get this as 158, and you can just put 00 here. So this is the value of n. Okay, so we this have 158 and 00. Next question, and it states that a compound microscope, the magnified virtual image is formed at a distance of 25 cm from the eyepiece. The focal length of its objective lens is 1 cm. If the magnification is 100 cm, the tube length of the microscope is 20 cm, then the focal length of the eyepiece lens is. So in this case we are given that we have an object, and image is formed at a distance of 25 cm from the eyepiece, and the focal length of objective lens is given as 1 cm. Therefore we can just draw a, you can say, two figures for that, and So suppose we are somewhere here, there is object, and we are given that the focal length of the objective lens is 1 centimeter. So let us suppose this is the f naught, 1 centimeter, and it says that from the eyepiece the distance of the image is 25 centimeter. So let us suppose we have the image that is somewhere here, I1, distance is about 25, and magnification 100, tube length is 60, and we need to find the focal length of the eyepiece lens. Okay. I'm missing something. A tube length is given as 20, so we get this will be our 20 centimeter, and somewhere here that will be our eyepiece focal length. So obviously there will be two images formed. One is our I1, and let us suppose somewhere here we have our I2, and from the objective let us suppose this distance is given as our U, and this distance of the image is given as V. So we have two lenses. So from the first lens we can say I1 is the image because of first lens, and I2 is the image of the second lens. So I1 is the image first lens, and our I2 is the image of second lens. So we can say for first lens we can write our 1 upon, let us call that as V1, and we have this is minus 1 upon U, that is a minus, is equal to our 1 upon F naught. So we get this as 1 upon V1, this comes as plus 1 upon U, and is equal to 1 upon 1. So this gives us that our 1 upon V1 will be equal to 1 minus 1 upon U, which gives us that our U minus 1 upon U. Therefore our V1 will be equal to U upon U minus 1. And the magnification, let us call for the sake of convenience this as 1, much more easier to differentiate. So we can say our magnification, that is for our M1, we are only interested in magnitude. This will be our V1 upon U1, and V1 upon U1 will be equal to 1 upon U1 minus 1. And for the second lens, this image will be acting as an object. Okay. Therefore we can say that our U2 will be equal to, we have this as 20, and 20 minus our V1 will be giving us a position of our object. So U2 will be equal to minus of 20 minus V1, this is our I1, and we substitute value of V1, we get this as our U2 will be equal to minus of 20 minus U1 and U1 minus 1, and our V2 will be equal to minus of 25 centimeter, Therefore, we can say the magnification that is m2, only magnitude. We can write this as our v2 upon u2, which gives us 25 upon u2, and the total magnification is said to be given as 100. You can say that total magnification that is of m will be equal to m1 into m2, which will be equal to 100. We substitute it, we get this as 1 upon u minus 1, and this comes as, that was our 25 upon u2 is our 20, so this comes as 25 divided by 20 minus u1, and u1 minus 1 is equal to 100. And now it is a simple calculation, and this comes as u1 minus 1, u1 minus 1 cancels out. We take the LCM and we get this as 25, and this comes as 20 times u1 minus 1 minus of u1 is equal to 100. And from here we can write this as 20 u1 minus, and we can say that this will be equal to 25 upon 100 is equal to, this will be over 20 u1 minus 1 and minus of u1. This comes as 1 upon 4. Therefore, we can write that 1 is equal to, we have this is 80 u1 minus 1 and minus of 4 times u1. So we just open the bracket, we get this as 80 u1 minus 80, and this is minus of 4 times u1. Now we can further write it. We have here 1 and here we have minus of 81, so this comes as 81 is equal to 80 minus 4, that will be over 76 times u1. So we get our u1 is equal to 81 upon 76, and we need to find out our u2. So we get our u2 will be equal to minus of, this is our 20 minus, and this is our 81 upon 76 divided by 81 upon 76 minus 1, which comes approximately will be equal to minus 19 upon 5. Now we can easily use the lens formula. We got our v2 as well as u2. Therefore, we can say that our lens formula, we get this as 1 upon v2 minus of 1 upon u2 is equal to 1 upon focal length of our eyepiece. We substitute the values. 1 upon v2 is minus of 25, and this comes as minus of minus plus, and we come this as 5 upon 19 is equal to 1 upon fe. So we get our fe will be equal to, this will be close to 19 multiplied by 25, and 25 multiplied by 19 will be our LCM, and we get this as minus of 19 plus, and we have this as 25 125. Sorry, this is 1 upon Fe. So this comes up 106. So we have a Fe will be equal to, we have this as 25 into 19 divided by 106, which comes approximately equal to 4.48 centimeters. So it comes as approximately equal to 4.48 centimeters. Next question. It states that the distance between an object and a screen is 100 centimeters. A lens can produce real image of the object on the screen for two different positions between the screen and the object. The distance between two positions is 40 centimeters. If the power of the lens is close to n by 100, depth where n is an integer, then the value of n is. So it says that it produces real image on the screen. Position of the screen will be fixed for two different positions between this of the lens. Okay, so we can just draw an approximate figure. So this is our suppose screen, and we have an object that is suppose somewhere here, and we have two positions of the lens. This is first position of our L1, and this is our second position, that is our L2. We are given the distance between the two is given as 40 centimeters. Okay. And the distance between the object and the screen is also given, that is our 100 centimeters. So let us say that the distance between the object and the lens L1 is our x, and the distance between the L1 and the screen is our y. Therefore, for location L1, that is, we can say that our object is, and the position, this is our screen. So the image is always on this screen, and image will be always at this position. So image is fixed position. Okay, whether the lens is at L1 or is it at L2. So we can say for position L1, we can have that our u, let us call that u1, is equal to minus of x, and our v will be equal to y. And focal length, let us suppose, is f, which will be same for both cases. So we can say that our 1 upon v minus 1 upon u is equal to 1 upon f. This gives us 1 upon f will be equal to, our u is our, let us suppose this is v1 and this is our u1. So we can say 1 upon f will be equal to 1 upon y, and we have this is minus of x, and this we can write is 1 upon y plus 1 upon x. Let us call the equation number 1. And for second location, so we can say position L2, for position L2, our u2 will be equal to 40 plus x, that is minus of 40 plus x, and our v2 will be equal to, that will be coming as y minus 40. Focal length will be same. So we can write it as 1 upon f is equal to 1 upon v2 minus 1 upon u2. We substitute the value. We get this as 1 upon y minus 40 minus of minus 40 plus x. And we can say this minus and minus becomes plus. Let us call this as equation 2. And this is also upon 1 upon f, and this we also have 1 upon f. So from equation 1 and 2, from equation 1 and 2, we get 1 upon y plus 1 upon x will be equal to 1 upon y minus 40 plus 1 upon x plus 40. Now we can just easily sort it out, and we can take the LCM. We get this as xy, and this is our x plus y is equal to, and here we have our y minus 40 and x plus 40. So this gives us x plus 40 and plus y minus 40. I hope the calculation is correct. 40 and 40 goes away, and we are left with x plus 40, x plus y, and x plus y also cancels out. So we get this as y minus 40, and this has x plus 40 is equal to xy. And if we open it, we get this as our xy, and we have this minus 40 for x plus 40 for y, and minus 1600 is equal to xy. And here xy and xy cancels out. So we get this as minus 40 of x plus 40 of y is equal to our 1600. Therefore we get this as 40 goes by this, we get this as minus of x plus y will be equal to 40. And we also know that our x plus y is equal to 100. We have our x plus y is equal to 100. So if we add these two equations, x and x goes away, so we are left with twice of y is equal to 140, giving us y is equal to 70. And if y is equal to 70, x will be equal to 30. This gives us that x is equal to 30. And we need to find out what? The power. So we found out our x and y, and we can find out the focal length. And focal length is 1 upon x plus 1 upon, 1 plus x and 1 upon y. Therefore we can say that 1 upon focal length will be equal to 1 upon 30 plus 1 upon 70, and this comes as 2100, and this is 70 plus 30 is our 100. So we can say our focal length f will be equal to 2100 divided by 100. So this goes by, we get our focal length, that is our f is equal to 21. Therefore we can say that our power is equal to 1 upon f, which is 1 upon 21, approximately equal to 4.76, and we are given that the power is equal to n by 100, which is equal to 4.76. This tells us that our n is equal to 476. So we get value of n is 476. Same question we can also solve by using the displacement method. Okay. You can say using displacement method, which gives that the focal length f is equal to capital D square minus small d square divided by 4 times capital D. And here capital D is the distance between the object and the screen, which in this case is given as 100, and small d is the distance between the two, which is given to us as 40. 40. And if we substitute it, we get up f is equal to 100 whole square minus 40 whole square divided by 4 multiplied by 100, and this will be approximately equal to, we need to find out the power, and which will be obvious, power and then be n, and we can say this will be equal to 100 minus this will be over 60, and this will be plus 140 divided by 4 multiplied by 100, and this comes as 100, and this will be 6 into 14 divided by 4 times 100. 100 and 100 goes away, and we can just sort it out. This goes by 3 and 2, and this goes by 7, equal to 21. Once again, same solution. Power is equal to 1 upon f, that is equal to 1 upon 21, which is our n upon 100 is equal to 4.76, giving us that our n is equal to 476. Okay, solution will be same. I think this completes all the question. Yes. So these were the question which was asked in the year 2020, and there are still some question left of the mains, and in the third part we are going to continue with the advanced and some questions which are left for the mains also. This completes all the questions for part second. Thank you.